Hello students, welcome to the lecture 6 in which we will do a few more examples how to use rectangles to approximate the area. So the first example we're going to do is is the following. Use inscribed rectangles to find the area under the curve so we'll take something a little bit more complicated, like compared to last example, like 9 minus x squared over the interval 0 to 3. So basically, let's try to make a picture. So we have a function which is x squared, but since we have a minus, it's flipped upside down and moved 9 units up. So basically, you have something like this. And if you plug in x equals 3 and x equals 0 into the function, f of 0 will be 9 minus 0, so it's going to be 9. And f of 3 is going to be 9 minus 3 squared, which is 0. So this is exactly x equals 3. So we want to find this area under this curve by splitting it up into the subintervals, right? So we're going to set up, usually the first thing to do is set up delta x. And our delta x by definition is b minus a over n. In our case, b is 3, a is 0, and n is on the bottom, so we get 3 over n. All right. So let's try to think. We're going to split it up into the different strips. Okay. And our first point is x sub 0, which is equal to 0. And our last point is x sub n, which is equal to 3. This is x1, this is x2, this is x3, dot, dot, dot. And one before the last one, like always, is x sub n minus 1. So what would be x sub 1 in this case? We know x sub 0 is 0. So we have to step delta x to the right. So we have to move delta x units to the right. So therefore, x1 will be 0 plus delta x. So in our case, 0 plus 3 over n. X sub 2 will be 0 plus 2 delta x, so it's going to be 2 times 3 over n. 2 times 3 over n. X sub 3 will be 0 plus 3 delta x, so it's going to be 3 times 3 over n. I'm not simplifying because I want to do something with it a little bit later. And dot, dot, dot. Xn minus 1 is 0 plus, as you understand, n minus 1, because you can clearly see that this one matches up with this one over here, which is not really written out, but it's there. This 2 matches up with this 2. This 3 matches up with this 3, and so n minus 1 matches up with this n minus 1. So we have n minus 1 times 3 over delta x. And obviously the last term has to be equal to 3. Let's see if we're going to get it if we use our formula. It's going to be n times 3 over n. Indeed, it matches up. It is 3. So we did everything right. So what we can say about our function, since our function which is 9 minus x squared, is decreasing on the whole interval 0, 3. The minimum value for f of x, the minimum value for f of x on each subinterval, where does it happen? Let's look. If we look at each subinterval, if we take some particular piece like this one over here, we can clearly see that the minimum happens at the right end point, right? And the same for the next subinterval, and the same for the next subinterval, because the function is decreasing. So the minimum is always to the right. So the minimum of f of x on each subinterval is at the right end point of each subinterval. So why do I do that? Because I have to pick point C. So the C1 is the minimum, the x for the minimum on the first subinterval, and it's going to happen at the right end point. So it's going to be x1. So this is x1, so it's 3 over n. C sub 2 will be x2 because it happens in the second point. This is first interval, second subinterval, third subinterval, and this one is nth subinterval. All right, and x2 was 2 times, and actually here I can say 1 times 3 over n if I want to. And here I can say 2 over 3n, and c sub 3 will be x sub 3, which is 3 times 3 over n. We can see the pattern. We can put 3 dots and say that for the last interval, c sub n will be x sub n, which is 3. Okay, so question is, can I write the formula for c sub k? Do I see what, if I change the index 1, 2, 3 by k, do I see the formula? And we already figured it out that 1 will match up with 1, 2 will match up with 2, 3 will match up with 3. So I can say k times 3 over n. This is any c that I want. If I want C5, I'll plug in 5 for k and I will know C5. If I want the last one, Cn, I can plug in n for k and I will get 3. Right? If I want the first one, it's going to be 1 times 3 over n. So this gives me all ck's for k changing from 1 dot dot dot, maybe 2 dot 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 n. All right. So if I know C in general, I can find the area of a rectangle with index k. So what do I mean by this? I go back to my picture and I complete it because it's not done yet. So I'll have to create the top. So I'll create the top at the right end point. Okay, so over here. All right, so each of these rectangles k, I can find the area in general. So in order to find the area of rectangle with index k, I have to take the height, which is f of c sub k, times the width, and the width is delta x. So in our particular case, it's going to be 9 minus c sub k quantity squared, that we used our function for the height. This is the height, and this is the base. All right, so times delta x. Now delta x is 3 over n. So for any rectangle K, this would be the area. So for the first rectangle, it's going to be C1 squared subtracted from 9. And the only thing left to do is to plug in C sub K. And my C sub K is this quantity. So it will travel and we'll put it over here. So let's try to see what we're going to get. Equals 9 minus K times 3 over n quantity squared, parenthesis 3 over n. So I know area of each such rectangle. And if someone tells me, could you find the area of all of these rectangles? Then I will just write in a sigma notation. K equals 1 through n f of C sub k times delta x, which is equal to, so this is the area of all of the rectangles starting from 1 through n. And this is my formula for this expression here. So it's going to be 9 minus K times 3 over n quantity squared, and this expression is multiplied by 3 over n. All right, then I have a couple of choices, so we can simplify this expression by doing some algebra first without touching the sum yet. So we'll have 9, then this expression we need to square, so it's going to be k squared 9 over n squared. And and it's multiplied by 3 over n. So then, since we have two different expressions inside, we can distribute this 3 over n and have it separate, and separate these two expressions. So we have 3 times 9, which is 27 over n. Then we have a minus, and then we have, I wrote k cubed, it's a mistake, should be k squared, obviously. So it should be k squared times 9 over n squared times 3. So if we take 9 and multiply by 3, we're going to get 27. And if we take n squared and multiply by n, we're going to get n cubed. And so that's what we get. And since we have a minus in between, we can split it and write it as two different sums. All right, so we have 27 over n minus the sum. K goes from 1 to n. K squared 27 over n cubed. All right, so now let's think about it. As we can see, 27 over here does not depend on n. So that does not depend on k, sorry, so it doesn't change, so it's a constant, and we have a constant multiple rule for the sum, so 27 goes out. But this n over here is some fixed number, it's just in how many intervals we split it up the area, so it also does not depend on k, so we can put it outside. So what's left inside is number 1, which we add up from 1 through n. Then we put the minus, and we'll also try to think the same way for the second sum. 27 goes out, n cubed goes out, so we're left with k squared, but k depends on k, right? From 1 through n. So let's try to do a little bit more. So we add a constant in time, so it's n times 1. So it's 27 over n times 1. Minus 27 over n cubed. And for k squared, we have to use the formula. The formula was n times n plus 1 times 2n plus 1 divided by 6. And that's what we're going to put over here. N times n plus 1 times 2n plus 1 divided by 6. Right, so we use this formula for this expression. All right, so let's see what we can cancel. This n and this n can go away, and so we're left with 27. This n and one of these n's goes away, and 27 and 6 we can divide by 3, so this would be 2 and this would be 9. So we have minus, we have 9 from the top, we have 2 from the bottom. In the numerator, we have n plus 1, 2n plus 1 divided by 2. 2 is gone, n squared. All right. So the only thing left is to simplify this numerator, and we will be ready for the limit. So we have 27 minus 9 over 2. So we FOIL it out. So we have parentheses, we have 2n squared plus n plus 2n plus 1. So we FOIL this expression, we still have n squared on the bottom. All right. So are we ready to take a limit? I think we're ready to take the limit. So we take a limit when n goes infinity of the sum of when k changes from 1 through n, f of c sub k delta x, and this is our answer for the sum. So we say limit n goes to infinity, 27 minus, and I will distribute this 9 through the expression. So I'll get 18n squared. Then we have n plus 2n is 3n, so we have 27n. And then at the end we have 9, when 9 times 1. On the bottom we have 2n squared. So since we have a minus here, it's going to be the limit of 27 when n approaches infinity minus the limit when n approaches infinity of 18n squared plus 27n plus 9 over 2n squared. And limit of 27 is just 27. And here we can use the ratio of leading terms. So it's going to be limit n goes to infinity 18n squared over 2n squared. N squared and n squared goes away. 18 and 2 gives us 9. So finally we have 27 minus 9, which is 18. And that's our answer for this problem. So another example that we would like to do is the following, that we can also use circumscribed rectangles. We use inscribed, but we can use circumscribed too. So we can also use circumscribed rectangles. Right, so basically to use circumscribed rectangles, instead of taking the minimum, we're going to take the maximum values of f of x. So if the maximum values of f of x in the subintervals occur in the points d sub 1, d sub 2, and we have again d sub n of them, we have n of them, then the sum k goes from 1 through n, f of d sub k delta x is an approximation by circumscribed rectangles to the area under the curve f of y equals to f of x. Right, and then if we take the limit, we're going to get the exact area. And the exact area is A equals limit when n goes to infinity of the sum when k changes from 1 through n, f of d sub k delta x. So on the picture, if we have some curve, instead of taking the mean, we're going to take the maximum. All right, so if we go from A to B, we split it up into the rectangles. And on each subinterval, we're going to take the maximum. So for the first rectangle, we're going to use this line to be the approximation, then this line to be the approximation, then this line, then this one. So we always take the bigger value, always take the bigger value. All right. And d sub 0 will be A. This is d1, d2, d3, because these are the intervals. All right, and B is d sub n. So it's exactly the same situation as before. So basically, if you take one particular rectangle and zoom up on this one, you get something like this. You get something like this. So this is interval k, and suppose this is our function. So we're going to take the maximum on this interval, and maximum point will be denoted by d sub k on the bottom. And here we have x sub k minus 1, and here we have x sub k, right? So this is our picture. So area of the rectangle, this little one, is this area in red, is equal to f of d sub k times delta x, right? So basically the height times the base. The same as before, but instead of taking mean, we take the max. So let's do our older problem from the previous lecture using the circumscribed rectangles. So in this example, we're going to resolve the problem from the last lecture by using circumscribed rectangles. So for y equals to f of x equal to x on the interval 1, 2, use circumscribed rectangles to find the area for y equals to x over the interval 1, 2. So let's go back and redo the picture that we did in the last lecture. So we have a straight line going like this. We want to go from 1 up until 2. And we're going to subdivide into the strips, and x sub 0 is 1, this is x sub 1, this is x sub 2, and before 2 we have x n minus 1, right? And 2 is equal to x sub n. So on each subinterval, we're going to take the maximum, so it's going to be something like this. All right, so next step is to define delta x, and it's always b minus a over n, so 2 minus 1 over n, so it's 1 over n. And since our function is increasing, since f of x is increasing, the maximum on each subinterval occurs in at the right end point. At the right end point. So before we do that, let's write out x1. x1 is 1 plus delta x, or 1 plus 1 over n. Again, it's the same as the last lecture. So second one is 1 plus 2 delta x. And then third one is 1 plus 3 delta x. And x sub n minus 1 is 1 plus n minus 1 times delta x, which is 1 plus n minus 1 times 1 over n. All right, and obviously x sub n is 1 plus n times delta x, which is 1 plus n times 1 over n, which is 1 plus 1, which is 2. So check mark, everything we've done right. And for the d's, for d sub k, take the right end point. Take the right end points. Why? Because the function is increasing, and so the maximum happens on the right side. So for d sub 1, we go to the first subinterval, we take the right end point, so we take x1. So d sub 1 is x1, which is 1 plus 1 over n. D sub 2 is x2, which is 1 plus 2 times 1 over n. Okay, and d sub 3 is, I said x1, yeah, this is right. x3 plus, equals to 1 plus 3 times 1 over n, dot, dot, dot. And the last one is d sub n, which is xn, which is 1 plus n times 1 over n, which is 2. So before I move on, I will write these intervals in a little bit better form. So I'll write it like this, because it's just easier to deal with. And if you're worried about d sub n minus 1, how it looks, then it's just x sub n minus 1, which is 1 plus n minus 1 times 1 over n, which is 1 plus n minus 1 over n. So the question is, can we create a general d sub k like we did in the previous example? For this, we have to match up each index with the number on the right side. This doesn't change, as you can see. It always stays the same, so we're not going to worry about it to match. But this one matches up with this one, and this 2 matches up with this 2, and this 3 matches up with this 3. So we can say 1 plus k over n. 1 plus k over n. And this is our d sub k. So like in the previous example, we can find the area of the rectangle K. So we need to take f of d sub k and multiply by delta x. So area times the height times the width. So our function is f of x equals x, so it's just going to be d sub k times delta x. And our d sub k is 1 plus k over n, and delta x is 1 over n. All right, so this is the area of the case rectangle. So the total area of all rectangles is just the sum. So we add all of them up when k starts from 1 and ends at n. And we add up all of this area. So 1 plus k over n times 1 over n. So let's try to find the sum. First, again, like in the previous example, we're going to distribute this 1 over n through the expression. So we're going to get 1 over n plus k over n squared. Right? And since it's a plus in between, we're going to split it into two different sums. So our sum will be for k goes from 1 through n, 1 over n, plus the sum goes for k from 1 through n of k over n squared. And if you remember from the previous example, we want to take constants and take them out. This expression does not depend on k, so we can take it and put it outside, and we will be left with 1 inside. And in the second expression, n squared does not depend on k, so we can take 1 over n squared and put it outside. All right, so now we just need the formula for sum of k's, and the formula for sum of k's, if you remember, was n times n plus 1 over 2. So that's what we're going to plug in for k. And for 1, it's just 1 added up n times, so it's just n. So we have 1 over n times n plus 1 over n squared times n plus 1 over 2. So this n and this n we can divide. One of these n's we can divide. Our final answer is 1 plus n plus 1 over 2n. And this is the area of all rectangles, which is an approximation. To get the area itself, we have to take the limit when n goes to infinity of the sum of f of d sub k times delta x when k changes from 1 through n. And that's our answer for this sum. So it's a limit when n goes to infinity of 1 plus n plus 1 over 2n. And as you remember, limit of 1 is just 1 plus the limit of the leading terms. So n and n we can divide, so it's 1 plus 1/2, which is equal to 3/2, which is exactly the same answer as we found in the previous lecture. So as you can see, this is a very hard procedure. The only way to deal with it is to struggle. And if you don't want to struggle, we have to create shortcuts. And that's the idea for the next week and the last idea for the semester, pretty much. So I'll see you next week. Do some homework. That's the only way to learn these things.